This presentation is on monitoring dose metrics from your fluoroscopic procedures. There are two reasons to monitor. The first is safety, that you want to avoid patients of a substantial radiation dose, but it took many months for the extent of injury to fully manifest. The other reason is to collect data that you're going to use to drive your process improvement projects. And that might be a group PQI project, a practice quality improvement project that you're conducting as part of your ABR maintenance and certification program. Or it could be that you simply want to improve, that you want to figure out how you can preserve the benefits of the imaging guidance during these procedures but reduce the risks. During the procedure, there are different ways to monitor. There's displays in the room. Here's an image of one of ours where there's a bar graph at the bottom left that shows heat units building in the tube. The next metric at 11.3 is Kerma area product, and finally at the bottom right is 1 milligray of reference point air Kerma. You can also walk out into the control room a little bit later in this procedure and see metrics displayed there. And here's a zoom in where there's reference point air Kerma at 38 milligray. This is a first approximation of skin dose. It can't be used as skin dose because if you're changing the angle of imaging or moving the patient on the table or moving the table up and down, you've moved where the reference point maps relative to the patient's skin. Kerma area product at 564.7 microgray meters squared is a measure of tube output, and it's what we would use if we wanted to calculate doses such as we might want to calculate a future cancer risk in a particular patient. Fluoroscopy time at 0.8 minutes clearly has limitations for assessing safety. It doesn't integrate how many images were recorded during that 0.8 minutes, nor the dose per image. So it has limitations as a measure of radiation use, but we found it actually quite useful to assess procedure difficulty. Alert levels. So what numbers would you be looking for? Well, NCRP suggests that at 3,000 milligray or 3 gray, there should be initial notification that this requires monitoring at least during the procedure, a subsequent notification when passing 4 gray, and 5 gray is considered a substantial radiation dose level, which will require some patient follow-up. You can also be monitoring dose area product. It's not recommended to be using fluoroscopy time, although they did supply numbers in case you're working in a room that doesn't allow monitoring of reference point air Kerma or dose area product. But you shouldn't be doing complex procedures in rooms without that recording capability anyway. The problem, though, is that during difficult procedures, the primary operator is typically going to be focusing on the fluoroscopy screen and not really divide attention to look over at the dose metrics. And this is where we've adopted sort of a teamwork approach where the technologists are the ones that are looking to see when we're hitting 3 and 4 gray and reminding us that we've passed 3 and then telling us when we've gotten to 4 and crossing their fingers that we're going to get out of Dodge before we hit 5 gray because we have to do extra paperwork when we hit 5 gray. When we hit 5 gray, we have communication. We have standard text that we integrate into our reports. It includes the reference point air Kerma dose metric. And there's different language, whether we're between 5 and 10 or greater than 10. We also have a pamphlet for patient education about what they can expect and where they should be looking on their skin. And the problem is since most of these skin entry points are going to be on the patient's back, it's really difficult for the patient themselves to monitor it, but rather to point out to someone else that can look at their back, looking for typically a rectangular area of erythema early on for a potential skin injury. We take the cases that go over 5 gray, and they're part of our quality safety conference. We meet twice a month for 30 minutes to go over cases that we can learn something from, and occasionally when we have the cases that go over 5 gray, that's part of the discussion. We monitor dose metrics on a continuous basis, and that's part of a graph that's shown as part of every conference. And when we have cases that go over 5 gray, it's an opportunity for a deeper dive. To emphasize the learning opportunities, it's part of our PQI process. We've adopted the approach to try and avoid shame and blame. The primary attribution error, it's well known in the safety literature. When it's my case that goes over 5 gray, that 6 gray case, it was because I was put in an impossible situation. This was the 350-pound TIPS patient. Of course we hit 6 gray. When it's your case that hits 6 gray, it's pretty easy to fall into, well, it's because you weren't watching, you weren't monitoring, you weren't being careful with dose. That's the primary attribution error. When it's me, it's because it's impossible circumstances. When it's you, it's a flaw in your character. We have avoided that. We're using the data to drive improvement projects. We're definitely trying to avoid the high dose cases. And we've been monitoring and collecting dose reports since April 2011. As we've added more rooms, we increased the pace of collecting dose reports, and we're now over 700 a month. And as you can see, with all the different cases, there's a cloud at the bottom levels, but you see occasional cases that exceed 5 gray. I was actually part of the one case that was at 13.4 gray. That was an heroic effort in a 350-pound patient to stop him from bleeding to death from an SMA injury. It was incredibly useful later on, going back through that procedure, looking at the dose report, digging through the data, and figuring out different ways to optimize radiation use when you're in extremely trying circumstances. We now are at the point where it's far less than 1 per month case of going over 5 gray. And we haven't had a case going over 10 gray for several years. As we're looking at the data, we want to use it to drive quality. And I like the quality definition of quality is conformance to expectation. That our patients have an expectation that we're not going to give them radiation injuries. We're not going to burn their skin. And so they really expect that our cases are less than 5 gray. But we should probably be a little bit even finer, have finer granularity. We don't expect PICC lines to get to 5 gray. We don't expect central lines to get anywhere near it. And so we've started to pull apart and look at expected values for different common procedures. And I'm showing you in milligray that filters, central lines, G-tubes, the 50th percentile is less than 50 milligray. It goes up a little bit higher for biliary drainages and bilateral percutaneous nephrostomy tubes, and it's substantially higher for TIPS and uterine fibroid embolization, and we'd expect that. And this is really an ongoing analysis of our data to try and establish expected ranges for common procedures. The way that data is generated is that we have dose reports that are written by the machine at the end of every procedure. They're collected in an archive, and now they're actually, we have a commercial software package that helps with data analysis at that end. On the other, we collect data through our radiology information system, the RIS. That's the procedure billing code, so it allows us to characterize what procedure was actually done. It tells us who was part of that procedure, who was involved as primary and secondary operators, and also the technologist supplies used, what room. There's an incredible amount of information captured in the RIS, and now we have a process where we combine dose reports with the RIS data and using that to calculate those expected ranges. For improvement, as we collect data, we want to compare the observed values that just came out of today's work to predicted values. And if we see a large difference, it warrants an explanation. Why is it that if our expected 50th percentile reference point error kerma for an IVC filter is 39 milligray, why was this case 400? And then plan strategies to try and reduce that difference between observed and predicted. And the only way we're going to tell if we're effective in our strategies is to allow the loop to keep running and collect more data down the road and see if we started to null that difference. And we're using tools from statistical process control, like these control charts. This is a method of monitoring an ongoing process. The software that created the graphs plots a average value of 125 milligray and calculates a control value that's unexpected, that a typical procedure would go above 460 milligray. And we had 2 cases that did. The bottom panel is a moving range, which is a method of monitoring case-to-case variation. The software has highlighted the 2 cases above the red line with a numeral 1 as one type of unexpected event, and then there's a series at the very end of 2s which are below the green line, which says that it's unusual to expect a series of cases to lie underneath the average like this. And this was an indication that when we changed our protocols back in September 2011, that we actually dropped our expected dose for the average and need to recalculate based on that expected change. So we've investigated events where we have points that are above that upper control limit. And here's an example from one of those. The software system that we have now allows us to create a procedure timeline looking at how radiation was used throughout this procedure. So on the bottom x-axis is the procedure time, and during this 15 to 20 minute procedure we see a series of spikes which correspond to DSA acquisitions. And so there are 3 separate DSA runs, each of about 60 to 70 milligray. And if you recall, 39 milligray is our 50th percentile for an average filter. So the first question is, what's driving each DSA run to be more than we'd expect for an average filter? And the second is, why are there 3 DSA runs? We can explain 2 when we reviewed the procedure. One was the typical one to map out the IVC. The second one was a retrievable, the one at the very end was a sequence to assess a retrievable filter to see if it was centered within the IVC and then available for retrieval down the road. But the third, whether it's the first or the second, wasn't quite clear why an additional DSA acquisition was performed. But looking at what was driving dose, this was a big patient. When we look at a CT that was done shortly after the filter was placed, this patient is 37 centimeters front to back, and that clearly attenuates the beam, markedly increases reference point error kerma, and it's not that apparent to the operator when they're doing the procedure. There's nothing on the image saying that we're sending in many photons and only a few get through to the detector. It would be much more useful if the tone for fluoroscopy were actually reflect the intensity of the beam. A low-level tone, sort of a rumble for someone who's thin and there's little attenuation of the beam, whereas a high-pitched and relatively irritating scream for when we're sending in many photons and only a few make it to the detector would be useful. We've looked at the different events that cause high doses in our filters, and the most common is large patients. We define obesity as greater than 30 centimeters front to back on a corresponding CT in the same region. We also saw a series of cases where CO2 was used as the contrast agent, and that clearly tends to drive up dose. We've had a couple of filters that, after they were initially deployed, were thought to be tilted enough that it would make retrieval down the road hard, and so the filter was immediately retrieved and redeployed, and those extra steps add fluoroscopy time as well as radiation use to the procedure. So in summary, we should be monitoring for safety. Skin injuries, it's difficult to avoid in the most complex procedures, but they shouldn't be a surprise through a combination of intraprocedural monitoring and reflection at the end of a case. We need a team approach because intraprocedural monitoring is difficult for the primary team. This is where the techs really help us out. Monitoring for improvement, we've started to develop an expected range for our common procedures and start to realize that when we look at outliers, that we probably need a different expected range for certain classifications of patients, such as the very large. Thanks.